So we already looked at combinations. Now let's look at what I'll call partmutations. Some people call these permutations, but I'll just call them partmutations. So let me define what I mean by a sequence being diverse. So let capital X be a set. Let's say little x is a sequence of length n made from the objects in capital X. We'll say that little x is diverse if all the entries are distinct. Here's an example of what I'm talking about. This sequence is not diverse. It's not true that all the entries are different. This sequence is diverse. All the entries are different. That's what I mean by diverse here. Now I can define what a partmutation is. Let's say capital X is a set. We'll say that P is a partmutation of X with length K if P is a sequence of length K built from the objects in X and P is diverse. So here's an example. Let's say X is a set of letters A, B, C, and D. If you want the partmutations of length 0 of X, this would just be the empty set. If you want partmutations of length 1 of X, this would be all the sequences of length 1 that you could write down using the objects from X. If you want partmutations of length 2 of X, this would be all the sequences of length 2 that you can build from X where you don't repeat any objects. So I've listed here all the sequences of length 2 that you can build using the object from X where you don't repeat any objects. If you want partmutations sub 3 of X, this would be all the sequences of length 3 that you can build using the objects from X where you don't repeat any objects. If I write partmutations sub 4 of X, this would be all the sequences of length 4 that you can build from X where you don't repeat any objects. So here's the basic fact for counting how many partmutations you'll have. So if the number of objects in X is n, then the number of partmutations of length k is given by this formula. So you do n factorial over n minus k factorial. And this shows up an awful lot, so there's a special notation for that. So I'll define nk with a star here to be this fraction. Other people will just write npk whenever I write nk star. You might also see pnk, that stands for the same thing. Here's an example. Let's say x is these letters. So x would be the set of these letters A, B, C, and D. Then if I want the number of partmutations of length 3, I'll just plug everything into that formula. So there's 4 objects in x, so we'll do 4 factorial over 4 minus 3 factorial. That'll be 4 factorial over 1 factorial. That'll end up being 24. So there's 24 partmutations of length 3 from x. And if you go back and look at this set here that I wrote out earlier, there's 24 sequences like that. Let's look at some examples where you use partmutations to count how many ways you can do something. Let's say there are 5 dogs in a competition. I want to know how many ways you can choose a first place, second place, and third place. So I've got 5 objects available. I want to take 3 of those objects and put them in a certain order. So this would be 5p3. So I'll write it as 5, 3 star. Another way to think of this is 5 times 4 times 3, and that'll give you 60. So the key to doing combinations and partmutations problems is that you'll use combinations when the order doesn't matter, and you'll use partmutations when the order matters. So here, the order that you put these dogs in will matter. So if you have the German Shepherd first, the Beagle second, and the Rottweiler third, that's different than the Beagle being first, the German Shepherd being second, and the Rottweiler being third. So the order matters when you do this, so we'll use partmutations here. Let's say there are 8 candidates running for president. I want to know how many ways you could choose a president and a vice president from among these people. So the order will matter here. Whether or not you pick the person to be president or vice president is going to matter. So the order matters. So there's 8 people available. I want to choose 2 of them and put them in a certain order. So we'll do 8p2. That'll give you 56 here. Let's say there are 10 silk ties for sale. I want to know how many ways I could buy a tie for me, a tie for my brother, and a tie for my dad so that we all get different ties. So I'll be buying a tie for each person. So you can think of putting the ties in a certain order, and the order would represent which tie goes to which person. So maybe the first tie goes to me, the second tie goes to my brother, and the third tie goes to my dad. So the order matters here. And there's 10 ties available. I want to choose 3 of them and put them in a certain order. So this will be 10p3. That'll be 720. Now I want to know how many ways 4 people could line up to form a group picture. So there's 4 people. I want to take 4 of them and order them in a certain way. So it's 4p4. That's the same as 4 factorial. That'll be 24. So there's 24 ways you could have 4 people line up for a group picture. Here's an example that shows the difference between combinations and partmutations. Let's say you have 9 sweaters. I want to know how many ways you could choose 3 sweaters to wear on Monday, Wednesday, and Friday. And then I want to know how many ways you could choose 3 sweaters to take with you on a trip. So in part A, the order will matter. So it depends which sweater I wear Monday, Wednesday, Friday. If I change the order of the sweaters, you could think of that as a different outcome. So here the order of the sweaters matters. So we're going to use partmutations. So that'd be 9p3. That's actually 504. For part B, I want to know how many ways I can choose sweaters to take with me on a trip. So here the order doesn't matter. I'm just going to take 3 sweaters with me. Doesn't matter what order they're in. So that's combinations. So we'll do 9 choose 3, and that'll be 84.